This is the Related Rates morning quiz review. Let's go through these problems here. Number one, a conical paper cup is 15 centimeters wide. 15 centimeters tall with a radius of 5 centimeters. Water is being poured into the cup at a rate of 32 cubic centimeters per second, and 32 pi cubic centimeters per second. At the moment when the depth of water is rising at 72 centimeters per second, find the radius of the water level at that time. So we're dealing with the volume of a cone, so V is equal to 1/3 pi r squared h. We know we have to go through similar triangles here based off of the fact that we are only given information about two of the three variables. So dv dt is given to us, dh dt is given to us. The water level is rising at a rate of 72 centimeters per second. So that's dh dt, so rate of change of the height of the water. So we set up a similar triangle here, the 5 and the 15 representing the dimensions of the cup, or of the container's right triangle here. And then little r and little h represents the water level at that moment in time. So we set up proportions to relate the two variables r and h. So small radius is to the big radius, so r over 5 is equal to the ratio of the small height, so height of the small triangle over the height of the large triangle, so h over 15. If we do cross product here, we get 5h is equal to 15r, h is equal to 3r, and so we have a relationship either solving for h or solving for r. So we have to decide. Let's see, what do we need to do? It says find the radius of the water level at that time. So we're trying to find what r is equal to. So we're trying to find what r is equal to. Well, since we have dh dt, let's just go ahead and set everything in terms of h. Okay? Because if we solve for h, we can always work our way back to r because we have something that relates the two variables together. So let's do everything in terms of h since dh dt is given to us. So the reason why we want to do everything in terms of h is because if we have our volume equation in terms of height, then the derivative for height will produce dh dt, and then this 72 centimeters per second will help us, will be able to be useful to plug into the missing variable. So we have volume is equal to pi over 3 r squared h. We want to get everything in terms of h, so that means we want the radius to disappear. We want to solve for r. We want to replace r. So we have h equals 3r, or r is equal to h over 3. We're going to take the h over 3 because we want to replace r. So r gets replaced in terms of h. So r squared becomes h over 3 squared times h. Now, at this point in time, we want to go through a set. We want to be able to clean this equation up. We don't want to jump into the derivative equation too soon, because we could, but but that would just make things harder because you're forcing yourself to go through product and chain rule when you could just clean this up and just rely on power rule. So if we clean this up a bit, let's see, h over 3 squared becomes h squared over 9. If we continue simplifying and reducing, we can pull the 9, 3, and the pi all out in front as a coefficient, so pi over 27. The h squared times h becomes h cubed. So now we have an equation that is a lot easier to manage. Right, so let's find the derivative now. V becomes dv dt. Pi over 27 is just going to be a coefficient. It's just going to attach itself to whatever the derivative is. So h cubed is what we're dealing with here. H cubed, the derivative going through power rule, bring down the 3, h squared, and then we're having to involve, find the derivative of h with respect to time. So we have to attach a dh dt. Continue cleaning this up here. dv dt is equal to 3 over 27 is pi over, or 3 pi over 27 is equal to pi over 9, h squared dh dt. So we have our derivative equation. Let's see what we can do to plug in. dv dt gets replaced with 32 pi cubic centimeters per second. H we don't have, so we're going to leave that alone. dH dt we do have, which is 72 centimeters per second. So now we can just solve for h. Okay, h is not what we're looking for. We're not looking for height, but if we can get to height, then we can go through this conversion formula to get to radius. So h, to solve for h, we're going to, if I divide both sides by 27, well actually 72 divided by 9, I can simplify this to be just 8, so 8 pi. Divide both sides by 8 pi, 32 pi divided by 8 pi is 4. 4 is our h squared, so h must be equal to 2, since we can't have height being a negative value, so I will have to take on the positive value. So h is not quite what we're looking for, but we can use this to help us find radius, because we have a relationship here between h and r. So we know that at any moment in time, height is going to be 3 times the length of the radius. So we know h is 2. So if h is 2, we can simply solve for r and divide both sides by 2. R is equal to 2/3 centimeters. Number 2, the area of a circle is increasing at a rate of 1 square centimeters per second. How fast is the diameter changing when the circumference is 2 centimeters? All right, so here are all the information that we need. Area of the circle is pi r squared, circumference is 2 pi r, diameter is 2r. Okay, so here's the area. Let's just go ahead and find all the derivatives of these equations and just have everything out in front of us, and then we can kind of pick and choose where the problem needs to go. All right, so let's go ahead and find the derivative. The derivative for a is dA dt. Pi will just hang out, it's coefficient, so the derivative for r squared is 2r dr dt. Okay, we'll come back to this. Now let's look at the circumference equation. Circumference equation is c is equal to 2 pi r. Let's find the derivative. So c becomes dc dt. 2r becomes 2 dr dt. Pi is just a coefficient. It will just attach itself to the front here. So let's see what's given to us in the problem. The area is increasing at a rate of 1 square centimeters per second. So we see the word area and we see the word increase. So that indicates that this number is referring to the rate of change of area. So the rate of change of area must be dA dt. So dA dt is 1 square centimeters per second. We see the word increase. So increase indicates that this value is going to continue to get larger. So if it continues to get larger, we're going to have to leave this as a positive. If we see the word decrease, then we're going to make the rate negative. Okay, so just be aware of that. How fast is the diameter changing? We're trying to find the rate of change of diameter. So we're trying to find dt. So, but the rate of change of diameter is going to be twice the rate of change of the radius, right? Because if we know diameter is 2r, if we find the derivative of d becomes dd over dt, 2r becomes 2 dr dt. So basically, if we can find dr dt, we can just use that to then find the rate of change of the diameter. All right, so we know circumference at any moment in time, or at this moment in time, is 2 centimeters. So if we know c is equal to 2 centimeters, we can use this and the circumference equation to find radius. Once we find the radius, we can use the dA dt to find dr dt. Once we find dr dt, then we can circle back to get to the rate of change of diameter. So we're basically using everything that's in front of us and trying to piece together how best to solve the missing variable. So in this case, the missing variable is solving for dr dt, because we know that dr dt will lead us directly to the rate of change of diameter. So we're going to find radius first. So circumference is 2 centimeters. So we know 2 is equal to 2 pi r. Divide both sides by 2 pi. Radius is 1 over pi. So if radius is 1 over pi, I can now go back and find my dr dt because I have my dA dt. So here's my dA dt equation. dA dt rate of change of area gets replaced with 1. R gets replaced with 1 over pi. dr dt is what we're looking for, so we're going to leave that as a variable. The pi's cancel out. We're left with 1 is equal to 2 dr dt. Divide both sides by 2. dr dt is 1/2. So if the rate of change of radius is 1/2, then the rate of change of the diameter must be double that, which is 1 centimeters per second. Number 3, an observer stands 700 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 900 feet per second. Assume the scenario can be modeled as a right triangle. How fast is the observer to the rocket distance changing when the rocket is 2,400 feet from the ground? So here's the observer standing at the corner of this right triangle. The launch pad is here, and the rocket is going to be launched directly vertical to the ground. And the distance between the person and the bystander and the rocket at any moment in time will be provided by z. So we have 3 variables related to one another. The size of a right triangle, so we know we can use Pythagorean Theorem here. All right, so we know that this distance x is going to remain constant. The horizontal distance between the person who's not moving and the rocket launch, which is directly vertical, will be the rate of change will be 0. So we know that we can just replace the x with 700. There's no need to maintain the variable here. We know x is changing over time, because as the rocket gets further and further away, z is going to be increasing. We know y is going to be changing because the rocket is moving. So the vertical distance between the rocket and the ground will always be changing. So we leave that as a variable. All right, so we're trying to find how fast the observer to the rocket distance changing. So we're trying to find dz dt, rate of change of the distance between the person and the rocket. So we can simply get to that by going through Pythagorean Theorem. So Pythagorean Theorem tells us 700 squared. So leg squared plus leg squared equals hypotenuse squared. 700 squared plus y squared is equal to 700 z squared. We know that the 700 is a constant, so the derivative of constant will go to 0. Y squared becomes 2y dy dt. Z squared becomes 2z dz dt. So now the only thing missing is we have dy dt. We're looking for dz dt, so we need y and z. So it says at the moment when rocket is 2,400 feet. So if y is 2,400 feet, then we can figure out what z is going through Pythagorean Theorem. At this moment in time, constant is 700. Y is 2,400. We go through Pythagorean Theorem. A squared plus b squared equals c squared. Solve for z. And we get z is equal to 2,500 after we take the square root. So we have our z value. So now we can just plug everything into our differential equation here. So y gets replaced with 2,400. dy dt becomes 900. Z, we just found that through Pythagorean Theorem, 2,500. And then now the missing variable is dz dt. Okay, so now we can just use our calculator to solve this. Divide the 2 and the 2,500 over. The 2's cancel out. The rest we can use our calculator to reduce. So dz dt, which is the rate of change between the observer and the rocket, will be 864 feet per second at the moment where the y value is 2,400 feet.